Okay, so this video is going to be the final chemical property of the transition metals, and it is the catalytic activity. So this video is going to be about the basics of the transition metals as catalysts, then it's going to go on to the heterogeneous catalysts, and it's going to end on catalyst poisoning, which is only an issue for heterogeneous catalysts. So, transition metals make good catalysts due to their variable oxidation states. There are two types of catalysts, there's heterogeneous and there's homogeneous. A recap on the definition of a catalyst is it speeds up the rate of a reaction by providing an alternative reaction pathway which has a lower activation energy without being used up in the reaction itself. Heterogeneous catalysts are in a different phase, or physical state, to the reactants. Reactions involving these catalysts occur on the surface of the catalyst, and we can increase then the rate of reaction by increasing the surface area of the catalyst. We can increase the surface area by using a support medium, and an example is in catalytic converters, where a thin layer of rhodium is coated on a ceramic support. This means that less catalyst is actually needed to create a larger surface area, and this is financially a good thing because that means you can use less catalyst and still get a faster rate of reaction. So it's financially a good option. There's three specific types of catalysts we need to know about, which are heterogeneous, and the first is the Cr2O3, which is the catalyst for the manufacture of methanol from carbon monoxide and hydrogen gas. You'll need 2 moles of hydrogen gas plus 1 mole of carbon monoxide in a reaction involving a Cr2O3 catalyst to produce methanol. The next catalyst is iron, and this is the catalyst for the Haber process. And we all know this by now, that's the production of ammonia from nitrogen and hydrogen gas. And for this reaction, we'll use 3 moles of hydrogen gas, 1 mole of nitrogen. The reaction will be using a solid iron catalyst, and it will form 2 moles of ammonia. Finally, we need to know the catalyst of V2O5, and this is the catalyst for the contact process. And this is where we form sulfur trioxide, which can be used to form H2SO3, which is an acid not quite as strong as H2SO4 sulfuric acid. This reaction is a two-step process, and in the first step we have V2O5 plus sulfur dioxide to form V2O4 plus sulfur trioxide. The V2O4 then reacts with half a mole of oxygen to reform itself as V2O5. Finally then is catalyst poisoning, and this is where a reactant, impurities, will bind to the surface of the catalyst. As I mentioned before, the reaction of heterogeneous catalysts occur on the surface of the catalyst, so if impurities are binded to the catalyst, this reduces the surface area available to the reactants. This in turn reduces the rate of reaction, and a key thing to remember how science works, time is money. Also, if the catalyst becomes that impure, it might need replacing, and catalysts aren't cheap. So, we need to know 2 examples of catalyst poisoning, and these are lead in catalytic converters and sulfur impurities in the Haber process. And you don't need to know much detail into it, you just need to know they are 2 examples. And to prevent catalyst poisoning, this is quite a patronising example, but you just need to ensure that you're using pure reactants. In all the mark schemes I've looked at, that's basically what they're looking for. It's a bit of an obvious answer, but it's easy marks. So that's it for the heterogeneous catalysts, the basics, and catalytic poisoning. In the next video I will go on to the homogeneous catalysts.